A few words about who I am. I am Alberto Ferrari, coming from Italy. I work at the SQLDay.com website, and we do problem-solving, complex project assistance. We design data warehouses. We write books. We are MVP, BI partners. We do a lot of things. I really like my job, but I know my job is sometimes a problem. And I can tell you exactly when it is a problem. At Christmas. Once a day at Christmas, I have a problem. You can imagine the typical Italian Christmas, all the family together, eating together, and mother asking me, come on, son, tell me once again, please, how do you earn your living? What's your job? And at the end, after many years, I ended up saying that, having an answer that is, I am an expensive consultant. And mother is happy at this point. She says, well, provided that you are happy and it's legal, I'm happy too. It was not a choice that of being an expensive consultant. It was easy because if you think at analysis services or doing analysis in the last few years, that meant using analysis services multidimensional. And multidimensional is not very user-friendly or BI professional-friendly. You need to create complex data structures. You need to create complex solutions. It requires highly optimized databases, expensive hardware. So the user was used to spend money on a project. And MDX. I mean, do you know, how many of you know MDX? And how many of you love MDX? MDX is hard to learn. It's hard to make it run fast. It's nearly impossible to optimize. You normally go on trying until it runs fast and you are happy. And so it was easy to be an expensive consultant at that point. And you can understand my strong disappointment when Microsoft came out with analysis tabular and DAX, saying that it's an in-memory database. It automatically compresses the data. It's amazingly fast out of the box. You don't have to learn anything. And the DAX language is impressively easy to learn, requires less modeling skills. So that basically would have meant that next year, my answer would have been, hey, mommy, I'm a consultant. And missing that word was a pain. But luckily, this is what Microsoft says. And I'm no longer your child. I know I don't believe in Santa Claus. I don't believe in the fairy thief. And I know that what Microsoft says is not really what happens in the reality. I've been working for a few years with Tabular, ranging from very small customers to somewhat large customers. And I learned some lessons. Xvelocity is really able to handle billions of rows, really large databases that you would not expect they fit in memory. But optimizing the columnar storage is not an easy task. It's something that you need to learn. And you need to learn the internals of Tabular in order to be able to optimize it. Otherwise, you will get poor performances. You need to, it's optimized out of the box. It means it runs very fast on adventure works, but if you have a larger database, as it normally happens, this is no longer true. Buying the hardware is near to a nightmare. It's very hard to buy the correct server that runs on that is able to run Tabular. And finally, the DAX language is easy to learn. It's very easy to learn, but mastering it, it's a completely different story. Requires a month of study, requires understanding of the internals, requires a lot of efforts. So what I want to share with you today is my experience, what I found, what I discovered, working with large tabular solutions. I will not try to teach you really something, just because 1 hour is not enough to teach you something. But the giveaway is the topics that you need to focus on and the points that you need to study further when you will have time and when you decide to go with Tabular. So we'll speak about how to optimize a columnar database in order to understand the difference between an optimized one and a not optimized one, and what you can get out of the engine. We will understand the distinct count issue, which we will understand it later, how to size the hardware, how to find, how to buy, how to forecast the memory footprint of your data model, and a couple of examples of DAX code that can be written in a naive way, so a very simple way. It works, but it works slowly, and how you should optimize. Of course, we will not have time to follow the optimization process. We will only see the first query and then the optimized query, look at the difference and try to understand what happened in the queries. And before we start speaking about all these topics, I want to briefly recall you what a columnar database is, what the Vertipack engine is. And there's a question for you is, how many of you know what a columnar database is? So few? Okay. Let's recap it briefly. You know that Vertipack is an in-memory database. Now they call it X-Velocity Memory Analytics Engine. I still call it Vertipack because it's easier. Vertipack is an in-memory database. Everything should be in memory. And it's a columnar database. To understand what a columnar database is, let's start recalling how data is stored by SQL, by any database engine. Imagine you have a table. Here it is ID, name, address, city, state, and balance due. Balance due is a column containing numbers. And if you are a SQL server, you need to store it somewhere on disk, for example. And if you want to store it on disk, you allocate some space on disk. You write the first rows. And when you are done, because the space is finished, you allocate more space and go on writing rows and writing rows and writing rows on different pages on disk, different segments on disk. This is the classical, the canonical way of storing data. There's nothing to learn here. It's the standard way all database systems since the 70s store data. It has some drawback. The main drawback is that if you want to compute the sum of balance due, then you need to scan on disk all these rows containing a lot of information which is totally useless for your query. All you are interested in is the sum of this column, and you need to scan everything in just to get one column. That's a pity because you spend a lot of time reading data which is not useful. But we know how to solve it. In SQL, if you have a database and you always want to get the sum of balance due, maybe grouped by state, what do? I heard it, just louder. Index. You build an index. That's easy. You build an index that covers the query containing the state, the balance due. So what is an index? An index is nothing but a reduced version of a table. It contains fewer columns, so it's smaller and it's faster to scan. If you think at indexing on steroids, so indexing everything, you do a column store. In order to do a column store, you start with the same table, but this time, instead of storing data row by row, you store data column by column. So you allocate some space for the ID, some space for the name, some space for the address, and each file contains only data for one column. It's like having one index on each column, and then you throw away the table. You just keep the indexes as your storage. What's the advantage of using this? Well, if I want to get the total of balance due, that's way faster because I don't have to read all this useless information. I focus only on a column and I grab all the data for that column. So it's way faster when reading data for a single column. Here, tables are stored column-wise. It's like pivoting on a table and storing it column by column. So it's faster when I read a single column. But that's not what I wanted to read. I want the sum of balance due grouped by state, so two columns. And of course, in such a scenario, I need to read the state column, the balance due column, and then join them at query time in order to rebuild somewhat a tabular structure that let me run the query. So basically, the columnar databases are faster when you read a single column and become slower and slower as soon as you increase the number of columns. Just to be clear, if you do a select star from a column store, you are likely to get worse performance than doing a select star from a table. But nobody does a select star, so this is not our problem. And moreover, in the BI world, we never do select stars. We always get aggregated data from a number of columns, the columns you put on the pivot table plus the numbers you put on the values. So this is a scenario where columnar databases really shine. And tabular is an in-memory columnar database. So I spoke about files here, but this is just theory. The same happens in memory. Think that from the CPU point of view, memory is as slow as it could be a disk. It's very slow, a couple of orders of magnitude slower than the internal cache of the CPU. So these are just arrays, areas in the RAM, and it's faster to scan a smaller amount of RAM than to scan a larger amount of RAM. That's very intuitive. Now, this is for columnar database. Now, in columnar databases, there are a couple of optimizations that tabular does and which are very important to learn and understand, which are run length encoding and dictionary encoding. Run length encoding is a compression algorithm. Since we are working with a columnar database, forget about all the columns. Focus on only a single column, because from the tabular point of view, the word is one column. Imagine that this is a column containing the quarter from a fact table containing billions of sales. Well, the string Q1 is repeated many, many times. For the first sales, all the sales in the same quarter have the same value. And it's not so clever to store the value so many times. So run length encoding simply detects when there are changes in the value, and instead of storing the strings, it stores a smaller data structure that says Q1 is valid from row 1 for, let's say, 310 rows. Then from the next row, there is a new value. This structure is way smaller than this one, because it's compressed. And if you do the same with the product ID, well, product ID works fine, but it changes more often. So there are different points where it changes, and the resulting data structure is slightly larger. You might reach a point, for example, with the price. The price changes so often that there is no point in trying to transform this data structure into this data structure. Tabular knows that and says, okay, if it changes so often, instead of trying to compress it, I store it as it is. This is the source of compression. Data in tabular is compressed because a run length encoding algorithm runs. And you can imagine that run length encoding is really depends strictly from the sort order, the number of, the way you sort data. If there are many, many repetitions, then it compresses very well. If there are not so many repetitions, then it does not compress well. The worst enemy for tabular are the primary keys. A primary key always changes, so there is no way to compress it in any way. Run length compressions, in any way, happens only when the size of the compressed data is smaller than the original size. And in reality, from my experience, it does not compress only primary key and a few other columns, but they really need to change very, very often. Then there is a second kind of compression, or second kind of encoding that happens, which is more important than run length encoding. How many of you work with analysis services multidimensional? Everybody, lovely. You know that in multidimensional you need to worry about the data type of columns. In any database you need to worry about the data type of columns. In any database, but in tabular. Tabular uses dictionary encoding. Let's go back to our quarter containing strings. Tabular says, well, these are strings, but I don't like strings too much. So I take all the distinct values of these strings and I build a dictionary containing numbers and the corresponding string. Then I replace inside the fact table each string with the corresponding number. What does this mean? That regardless of the data type of your source column, everything will be converted to numbers. So your tabular is totally data type independent. It does not really matter whether you store a floating point value, an integer value, a string, or whatever. Tabular removes any kind of data type and always builds this dictionary. Moreover, because it knows how many values are present, how many distinct values are present into that column, it uses the minimum number of bits required to represent the value. So if you have a column that has a lot of distinct values, the number of bits will be higher. If you have a column that has a fewer number of distinct values, the number of bits will be lower. That's pretty easy. Then, if you run length encode the dictionary encoded version of your column, so you run length encoding on these numbers, you build a compressed version of the dictionary encoded version of the column. You take these two items, the dictionary and the run length encoded version of the dictionary encoded version of the column, and this is what Tabular stores for each column. So if your table has 100 columns, you have 100 dictionaries and 100 segments. We call them segments that contain the real data. Then it's up to the engine doing all the conversion runtime. But the good point here is that it always works only on numbers, and CPU like numbers. They are used to crunch numbers. And it's compressed, so it's smaller, and Tabular is able to work well. Okay? Now, I imagine that you worked for many years with multidimensional without ever learning about how multidimensional stores data inside its memory. Or at least I did it. I worked for many years with MDX without having no idea how data was stored inside my engine. Because it was not needed. It was not so important. It was important only for extreme optimizations. In Tabular, it is incredibly important to know all these details in advance, before you start your first project. Otherwise, good chances are that you will have a failure, you will have problems, because you don't understand what's happening under the hoods. The key of Tabular, in order to reduce the memory footprint, so why do we want to reduce the memory footprint? Because we use less memory, which is always nice. But remember, scanning a smaller amount of memory is faster than scanning a larger amount of memory. So reducing memory has a strong impact on the speed of the engine. If you compress a column very well, it will be faster. If you don't compress it, it will be slower. That's as easy as it is. And how do you reduce the memory footprint? There is a single rule, which is the only really important rule. Reduce the number of distinct values of your column. Believe it or not, I save many customers by working with them for no more than 10 minutes. Because I simply go to the customer, look at the data model, look at the fact table, discover that they are storing the primary key of the fact table inside the data model, remove that column, and the problem is solved. Because the table immediately becomes half the original size. So you need to reduce the number of distinct values of columns using some standard techniques, some standard way of reducing distinct counts. This will increase the scan speed, increase the filter operation. And if you have a limited amount of time to work on a project, or if you want to search for the, how they call it, low-hanging fruits, now it's very common. If you're searching for the things that you can solve very quickly, you need to focus on the most expensive columns, which are the ones with a higher number of distinct values. Let's take a look at how you can do that. I have a database on this laptop that contains a few billion rows coming from a customer. And if you want to get information about the amount of memory that your Tabular instance is using, you have several options. There are the hard ones. You can run queries, you can look at the storage in the folder where Tabular stores all the information, or you can download a workbook that Casper de Jong wrote a few months ago, and it's available on the web. This workbook contains a Power Pivot data model that runs queries against the server, grabs information about how columns are stored, it grabs information about the memory footprint of each column, and then shows that inside the pivot table. All you need to do is open the workbook, click on refresh. Right now, the Power Pivot data model in the Excel workbook is querying my analysis services engine, retrieving data, and now it says, hey, this is the instance you are working with. It has 14 gigs. Is there a way to remove it? Yes. It has 14 gigs which are used, and you can, of course, expand. There are several databases. The database I want to look at is this, audience. Audience contains many tables, and our first goal is understanding where is memory, where are the columns that are using more memory. So we go for audience, then go to dimensions. It's a fact table in reality, but you know in Tableau there's no concept of fact table, so they call everywhere dimensions. This is the fact table, 13 gigs of RAM. And if you go below it, at the column level, now you have the columns which are in the fact table. Let's highlight them in some way. These are the columns in the fact table, and for each column I have the amount of RAM which is used by the column. Age, that's the age of the customer, the data, its ID, the network he was watching, the point in time. This is the time, this is the date, and then other columns, other useful, more or less useful information. Now, a first question for you. Why date uses so less memory and time uses 6 gigabytes of RAM? Louder.
Problem with the data, not the problem, difference with the data type, right? The difference between the data types.
No, they are the same. I told you 3 minutes ago. Tabular is data type independent. We don't worry about data types.
We have less dates than the times.
But unfortunately, that is not true. That's a good trial, but they have more or less the same number of distinct values.
Random encoding. There are many distinct values.
They are the same.
They are ordered. So date time is compressed using random encoding. Easier.
The problem, yes, you got the point. The problem is sorting. The date changes slowly. We have 4 billion rows inside this model, but the date changes very slowly. We are 4 years of data. The time changes very frequently. Each row has a different time. And the difference is between 0.37 megabytes and 6,000 megabytes. It's huge. What does it mean? Well, you need to choose which columns to optimize. You cannot optimize both date and time. You need to take a decision between them. And if you take the wrong decision, your database will be huge. If you take the right decision, the database will be very, very small. But looking at sides is one side of the story. There are many columns here. We have data, we have network time, many other columns. But you see that time is the most expensive one. Can you imagine a way, for example, to reduce that memory footprint?
Sort,
aggregate,
split.
Sort, aggregate, split. Elaborate further.
Remove.
Sort is not an option. We decided to sort by date because of so many other constraints. So you cannot do anything for sorting.
Don't use time.
Don't use the time. If you are able to convince the user that the time is useless, that is absolutely fine.
Can you introduce time span?
This is measured in seconds. It's the number of seconds from 00 to 24. It's just number of seconds. The easiest way, which is not so intuitive, I totally understand. At the beginning, I was completely, I was not understanding what was happening. It was so less intuitive. If you want to remove the problem, you only need to ask to your user, hey, but do you really want to do analysis at the second level? Can we do analysis at the hour level or at the 10 minutes level, which is normally enough? By reducing from the second level to the 10 minutes level, you reduce so much the number of distinct values, and you increase so much repetitions that this number will be probably cut by, you will probably remove the 6, and it will be only 192 megabytes.
1,440 minutes per day.
Yeah, you reduce it really a lot. And you don't change the expressivity of the system. It's the same system, same scenario, same everything. The point is that you don't need to focus on the data type, you need to focus on the number of distinct values and on the repetition. This problem, or let's not call it a problem, but this scenario is more evident if you run a few queries on it. For example, this query simply counts the number of rows. I never remember. We have 4.4 billions of rows in this fact table. Of course, needless to say, if you don't work with billions of rows, well, all these considerations should be very relaxed. Tabular is good on small databases, but on large databases, things are different. If you compute the sum of the age is a column with a very small number of distinct values that doesn't change very often, luckily. So it takes some time. If you want to take the time to understand the execution time, you need to run the profiler, connect to your data model. Let me see if I'm completely lost and I don't remember. No, I'm doing the right demo, okay. You connect with the profiler. You don't run profiler against SQL Server, but against analysis services.
Small difference, but
Sorry?
small difference, but better results.
Yeah. And from here, let's clear the cache. Then you compute the sum of the age, for example. And in the profiler, you will see some numbers. Basically, the numbers you need to focus on are the duration and the CPU time. Generally speaking, duration is smaller than CPU time because you have many cores, they are running in parallel, so you have a larger CPU time and a small duration. Then there are many other considerations about formula engine, storage engine, and other considerations, but we don't have time to cover everything. The point is only looking at duration. How much time does it take to scan that column and grab the number of this to compute the sum? If you do that on the age, it takes some time. Here it's 226 milliseconds. If you do the same on the time, it runs, and it takes 2.5 seconds. You see that the difference is huge. It's 10 times slower. Why that? Just because you have not optimized the column in the correct way. You cannot always choose everything in the model. You always have to take decisions. But these decisions are important because if nobody wants to sum the time, but that's just an example of a column. Scanning a column that contains a lot of distinct values that change very often is very expensive, while scanning a column with a lower number of distinct values is very fast. If you do that with the date, for example, we have seen that date compresses very well. You run it, and it's taking 16 milliseconds. So the real difference is between 16 milliseconds and 0.5 thousand milliseconds. It's huge, and it only depends on the optimization. If you don't know the internals, you will not understand how to optimize it, and if you don't optimize it, you will get poor performance, which are better than multidimensional, but they can be way better if only you spend time understanding the engine. That said, now I want to show you a couple of other queries. This is pure scanning. So sum is just a scan of the column. Do the scan and the job is done. So it's strictly dependent only on the memory footprint. But imagine you want to compute the distinct count of a column. This time you are no longer only tied to the size of the column or the memory footprint, but even on the number of distinct values that there are there, regardless of the sorting or somewhat regardless of the sorting. So you can run the distinct count of the age, and distinct count of the age runs in 170 milliseconds. You can do the same with the time, and it takes sometimes more or less 10 times more. I want to show you only the distinct count of the date, then I have everything in a slide. Again, distinct count of the date is 20. The number of distinct values of the date and of the time are the same. They both have 1.5 thousand distinct values. So sum is useful to get a feeling about how fast it is to scan memory. Distinct count uses different timings. Now, I don't have time to show you all the details of the query. So I prepared a slide, which I guess you will not be able to read from the bottom. These numbers are taken from on another server, but the orders of comparison is the same. Age, for example, uses 200 megabytes, time 6 gigabytes, weight 3 gigabytes, 2.7. The number of distinct values of the weight is very high. Summing is pretty... No, let's start from the beginning. Time, the most optimized column, has 1.4 thousand, yes, values. It takes 1.3 seconds to do the sum and 845 milliseconds to do the distinct count. The data has the same number of distinct values, but sum and distinct count are way faster just because of sorting, memory footprint highly reduced. Weight is smaller than the time, but the number of distinct value is higher. So for the sum, which is just a scanning of the table, it's faster. It's half of the time of time, because the memory footprint is half that of the other column. While distinct count is slower because of the large number of distinct values it has. There are so many distinct values that scanning it and computing distinct values is slower. The question is, should you worry about all these? And the answer is yes, you should. Because it's the only thing you can do to optimize a tabular solution. You cannot buy better disks. We don't use disks. You can buy better memory, but you already have the best memory. You have already the best CPU, and if you want to optimize it, you need to worry about all these details. How do you reduce the distinct count? Well, reduce the precision of numbers. If we are speaking about dollars or euros, or how do you call your money? Zloty? Zloty? Then you cannot, of course, reduce precision. But I've been to a customer that was using the duration of events stored as milliseconds. And that event was a phone call. Now, do you really worry about milliseconds at the phone? No. We moved from milliseconds to seconds, and then to tenths of seconds doing several trials. But just moving from milliseconds to seconds reduced so much the memory footprint that the customer was happy. And the solution comes in really 5 minutes if you know the beginning. If you don't know the beginning, you simply look at it and you don't understand what's happening. If you have date and time, If you have datetime column, get rid of it. Datetime is your enemy. Date column, time column, smaller number of distinct values, higher number of repetitions, better storage, faster engine. And then there are other techniques, but they are too fancy. Now, you know how to compress memory, to optimize a column, and the customer says, I'm happy, I want to buy tabular, you convinced me. Now I need to buy a server. What server should you buy? How much memory is required for your data model? Because tabular does all the compression you have seen, I cannot tell you, as Microsoft does, that the average compression ratio is 10x, because that's not true. We have no idea of the compression level you can achieve. The only thing you can do is try it. Take your data model, try the compression, take your data model, optimize it, and then start adding rows in order to understand how many rows, how many megabytes you will need. So you build the first prototype, you add 10% of the rows of the fact table, you process it, run the biz memory report, that workbook you have seen a few minutes ago, and look at the size of the dictionary and the size of the segments. Understand where is your memory, then starts adding more rows, and then more rows, and then more rows again. Once you have 6, 7, 10 dots, so 10 evaluation of the memory footprint, you can connect the dots and draw a line. That is your forecast, or how much memory will be needed for the full model first. And then spend your time asking your customer the most important question, which is, for how many years do you want to run this system? If the answer is 5 years, then you need to predict the size of the model in 5 years and buy some hardware which is able to accommodate the growth over the years. This is important because you cannot simply say, well, it fits into 100 megabytes or 100 gigabytes, so buy a machine with 128 gigabytes and you are happy, because after 6 months it will be out of memory. And adding memory is not something that you can do easily. You cannot buy memory and put it on the server. A server comes on the market with a specific amount of memory, and most important, with a limit on the total memory you can install on the server. You cannot install all the RAM you want. You can buy disks, but you cannot buy RAM and install it. So RAM is a limited resource, not in the meaning that you cannot buy RAM. Today you can buy a server with 2 terabytes of RAM, and you can, somebody comes there, installs it, and it runs fine. But at some point you need to add a couple of terabytes more. That's not an option. So it's a limited resource. You can have as much RAM as you want, but up to a specific boundary. Worse, if you want to have only, let's say, 256 gigabytes, well, only. If you want to have some RAM, then you can install it on a laptop or a notebook or on a standard PC. But if you want to have RAM in the orders of magnitude of terabytes, and believe me, we are buying this hardware, we are installing this hardware, then this hardware starts to be NUMA. How many of you know what NUMA stands for and what is the NUMA architecture?
Non-uniform memory access.
Non-uniform memory access, but I haven't seen many hands raised. NUMA is important, and it was not so important with multidimensional. Basically because with multidimensional, nobody ever bought a machine with 2 terabytes of RAM. It was useless. With tabular, it is likely that you will encounter these machines. And if you encounter them, they will be NUMA. What is NUMA? Well, we'll come to this later because I started speaking about NUMA, and then we go back to the previous slide. NUMA is an architecture where if you want to build a machine with 2 terabytes of RAM and 256 core, can you imagine 256 cores scanning the RAM and computing values? What is the bottleneck of this architecture? The RAM bus. 256 cores are scanning RAM, and they will fight in order to get access to the RAM bus and get the next piece of RAM. So it's impossible to build large machines with a single RAM bus. NUMA answers to that and says, well, that's not a problem, we add more RAM buses. So instead of having one RAM bus, I build nodes, node 0, node 1, node 2, node whatever. Each node has a limited number of CPU and some RAM, a few gigabytes, a few 100 gigabytes of RAM. So if this CPU want to get RAM from its node, it's very fast and gets RAM immediately. There is less contentions on the RAM bus. But what happens if this node want to get RAM which is there? Because remember, even if it's a NUMA box, it's a single PC. So from the operating system, it's just one computer with no idea about where the RAM bus is. If this CPU want to get access to this piece of RAM, then it needs to go through the NUMA bus, the inter-socket connection or NUMA bus, which is a bus that connects all the nodes. It has only one drawback. It's slow. It is not as fast as the bus node, which is here. So it works, but it's slower. What's the problem with NUMA? The problem with NUMA is that if you run a query with tabular, if you run a query with tabular and you have all the cores running and they are scanning a memory which is on a remote node, then you are in trouble because tabular will start to slow down. Running tabular on NUMA node is a problem. Tabular is not NUMA aware. A software is NUMA aware if it is able to run on the same node and try to prefer the RAM in the same node. If you run on the same node, then it is fine. If you are not on the same node, then performance are bad. Microsoft says that less than 4 nodes is good, more is bad. But if you are searching for optimal performance, the rule is 1 node is good, more than 1 node is bad. That means you need to be able to run each tabular instance on a single NUMA node. How do you solve it? Virtual machines. You take a large NUMA server, you split it into different virtual machines. Each virtual machine runs on only a single NUMA node, and there it computes all its values. It has a very low impact on performance. Tabular works very well in virtual machines. But that means you need to be able to partition your database into different databases, each one handled by one instance. This is normally the case. It's possible to do that. But you need to worry about it. And for the hardware, when speaking about the hardware, if you need to buy hardware that runs tabular, you need to worry about the fastest cores you can find. Really the fastest. Go to the local shop and buy the fastest core you can see on the market with the largest cache. Because remember, the cache is faster than the RAM, so running on the cache is better than running on the RAM. The number of cores is not so important. It's very hard to see tabular runs on more than 8 cores, because the bottleneck is always the RAM bus. All the cores are scanning RAM, and the RAM is not fast enough to provide data to the CPU. When it comes to the disk, don't even think about the disk. Disk is totally useless for tabular. We don't use it. So there's no point in spending your money on disks. And good chances are that your customers will already have a server in-house which is optimized for multidimensional. Try not to use it, because the kind of server you use for multidimensional is totally different from the server you use for tabular. And I personally have talked with customers that told me, we already bought the server, this is where we need to run. And I had to show them that on their server, tabular was lower than on my laptop. At that point, they decided to change the server, which is true. The laptop, being a consumer product, has a very high CPU clock, lower number of clocks of CPU, but it runs very fast, and it's perfect for tabular. Optimizing is another topic to cover. DAX can be optimized in a different way than MDX. With MDX, optimization means try. If it doesn't work, try MDX Studio. If MDX Studio is not enough, write an email to Marco Russo, Chris Webb, or somebody else trying to get some information. If they are not able to solve it, then go on trying. You don't have many other options. Or you start reading fancy blogs with complex formulas and strange things. With Tabular, you have other options. Basically, you have a query plan. So you can look at the query plan of your DAX query and try to optimize the code. The point is that it's not so easy. It is very hard. If you are interested in optimizing, I wrote a couple of white papers on SQLDay that introduce the task of optimization. So we start with very simple queries and we try to explain what are the points that you need to worry about. Why optimizing is important? Well, because you not only need to run a single query faster, but if you run in a large environment, you have hundreds of users which are constantly scanning and querying the data model. And Tabular is different than multidimensional. Tabular uses all the core 100% for a small amount of time. But you cannot have 100 users running 100% all the core. So your queries need to be very fast and do a very good usage of the cache. Remember, when it will be time to give a price to your customers, for the ones of you who are consultants, optimizing DAX is much more expensive than you might think. You will never be, unless it's very easy. If you really want to get the most out of a single expression, you will need to spend a few days on that expression alone, understanding exactly what happens under the cover and optimizing it. The results that you can see, of course, are amazing, but you need to spend time there. As an example, I want to show you the calculation of events in progress. Events in progress is a very common pattern for insurances, for manufacturing, for many different scenarios. Basically, imagine you have a machine that processes objects. An object enters, is handled, and then goes out. Or you manage orders. Somebody orders me something, then I work on the order, and when I'm finished, I ship it. During the time between the order and the shipment, that order is in progress. And my goal is counting how many orders are you handling now, or for insurance companies, how many insurers do I have now? What is my risk? How many people might I need to pay in case of a tornado, for earthquake, or something like it? If you're not familiar with DAX, this is not very easy to read, but basically this computes for each date the number of sales, the number of rows in the fact table that are where that data is greater than the order date and smaller than the ship date. So it's the number of orders which are open at a specific point in time. Okay? And this is how everybody, me included, would write the query after having followed a DAX course or after having learned something about DAX. We will see, skip this part because we have already seen it. We will see 4 different versions of the same query. The first one is the naive one. Then we start looking at, understanding that Tabular is a columnar database, and we change the way the query runs. Let me just clear the profiler and open events in progress. Can you read it from the bottom? Good. This is the naive query, and this is running on AdventureWorks. I better run it because it takes some time to execute. This is computing for each day the events in progress. And you can see that CPU is somewhat running, memory is being used, but not so much. But it's running and running and running and running again. Anybody has an idea where's the problem in this query? We have to wait 10 seconds more. Or if you want to optimize the query, how would you do it? It took 25 seconds at the end to execute everything. You are not expected to know the answer, so just speak.
Maybe conditions.
Condition, but what's the problem with these conditions?
Maybe they're calculated separately? Or?
Tabular is a columnar database. He likes columns. He doesn't like many columns. So if you rewrite the query, let's clear the cache so we are fair and we don't do any mistake. If you recompute the query in a different way, you do the filter on the order date and the filter on the ship date as two different scanning. This query runs in, I don't remember how much. What happened? Yeah, that's Windows 8. I guess you love it. 1 second. That's beautiful, from 20 seconds, 1 second, just by removing the scan on two different columns. And to do that, all you need to remember is, hey, Tabular is a columnar database. I need to work on a single column. 2 columns is bad. 1 column is good. Easy. Then what happened is that Chris Webb, you know Chris Webb? He's a smart guy, a friend of mine. But the real problem is that he found a better formula. Right now, the profiler, you see, it was 24 seconds, then 1 second. Then Chris Webb started working. This returns the same result. Oh my God, 158 milliseconds. You can understand the pain I had at this point.
Still your friend, or?
Absolutely.
It was the first.
Let's say that at that point it was no longer so much a friend, and I had to work to count it again between my Facebook friends. What I had to do is take his query, spend 4 days working on the query, building the query plan, understanding what was happening. Now I'm joking, but it's just to give you an idea of the effort which is needed to optimize. I spent 4 days looking at his query, running it, understanding the query plan, and then writing DAX formulas which are more similar to the final query plan and optimize slightly the query. And this query, which is absolutely not intuitive, counted again Chris among my friends, because I've been able to go half his speed. The point is not, of course, the war between me and Chris, which does not exist. The real point is you start with 24 seconds, and you can reach 73 milliseconds, which is huge, same result set. But it takes a lot of time. So is it worth doing it? I'm not sure about it. It really depends. It really depends on what you need to do. The naive query is 20, these again are numbers took on a different computer, but we go from 22 seconds, less than 1 second if you think in column way. Use the days between 156 seconds if you read the Chris Webb blog where he wrote the formula and explained it. 78 milliseconds, but it requires days of optimization. Is it worth doing it? Not for the vast majority of the formulas. But if you have a large system with a lot of users and you really need to nail it down and understand everything about that, keep in mind you can get a good result, but it's really, really hard. It's not easy. It takes a lot of time. But the good point is that you can do it. You can reach performance which are absolutely awesome. I have never seen an engine running that fast. On this pattern, which is, I guess, the most preferred pattern. Whenever we have a new engine, both me, Chris, and Marco, we try event in progress because it's a very nice pattern. And finally, remember that DAX is not complex, it's just new, it's a new language. We don't have much experience on DAX. It's simple, but it's not easy. Learning DAX is something that you can do in a couple of days. Mastering DAX requires months because you need to shape your brain in DAX. Writing good DAX always requires thinking in a creative way, thinking in a columnar database way, thinking in a different way than you are used to do it. And don't trust any golden rule. If you read my blog, if you read anybody's blog that says, whenever you are in this situation, do this, don't trust him. Me neither, because it's very likely that it is wrong. The last example that I want to show you, I know that I'm out of time, but I just want to know how much I'm, no, not yet out of time. Beautiful. On a table that contains 4 billion rows, knowing that the weight column has 1.5 million rows. Looks like being at school. Now having this problem with this number, what would you do at this point? So you have a table with 4 billion rows. Weight has 1.5 million rows. For the ones of you who know DAX and can read it, of course, is it better to write a SUMX, so an iteration with an if, or use the calculate function and put the condition there? Yes?
In my opinion, the left-hand example...
You need to know that I don't know the difference between left and right, so I need to go there, look left. This one
is worse.
This one is worse.
Because if statement compares values on a, I would say, row level. So
yes, it's iterating.
It's iterating. Every value has to be compared toward the 300,000 value.
Okay, so you say this is worse.
This,
other ideas?
in my opinion, is worse.
This is worse.
No.
Other idea? This is better?
Yes.
Why?
Because first you have quick if and then sum.
It's called column focus.
Yeah, but it's iterating over 4 billion rows. So this is iterating 4 billion times, computing this value.
No, this is opposite.
Sorry?
It's column.
Yeah, but it's 4 billion rows anyway.
It's compressed.
Yes, it's compressed, but not so much. No, really, weight changes pretty often. So compression is not the key here. The point is that if you follow one of my courses, and if you learn everything, and if you read all my books, your answer should be, this is worse. And I can prove it because I asked it to Marco Russo. I sent him the query and say, which one is the best? And of course, he says, iterating and running if is absolutely bad. If you want to get top performance, you need to run this way. And I tried it, of course, because that was a customer of mine that had a problem. I skip all this part. I just want to show you. Okay. This version is the version with calculate. How does this expression compute the value? It takes the audience weight, the column audience weight, scans it, creates a bitmap, then applies this bitmap to the fact table and scans everything and computes the value. Generally speaking, it's the fastest way to compute anything in tabular, because you scan only the column store, you build the bitmap, you apply to the engine, to the data model, and then you compute everything, and it's faster. The problem is that if you analyze the query plan of this, which we cannot do, but if you do it, and you run this query on the correct database, it gives a result here, and the highest time is spent in scanning the audience weight column, which changes very often. It's not so well compressed, and so it's pretty large. And it took
616 milliseconds, which is too fast, I guess. Oh no, it's not equal 30,000. Sorry, it's...
The difference in the square because there's equal to 200.
Yeah, but I made the wrong thing. It's always the same, the last demo doesn't work. No, I took the wrong column. I needed to use this one.
It's greater than 30,000. Using equal, it's too fast. That was too fast. And I say, well, what's wrong with the demo? You see, it's computing. If you look at this, is using all the CPU. It's doing all the scans. And now it eventually ended in 10 seconds, which is way better. If you look at the profiler, 6 seconds are spent only to get the distinct values of the audience column scanning the column store, because it's a large column. So it first scans the audience, the weight column, get the distinct value, then builds a bitmap, applies the bitmap, and the final result is this. The execution time is 9.4 seconds. This demo is not exciting as other ones, so I'm not going to get the same difference in performance, but I want only to show you how non-intuitive it is. This is doing a different thing. It is scanning the table and checking row by row if the row is greater than 30,000. The difference is that it doesn't have to build the bitmap in advance, but it simply scans the table in a very simple way. If you run it, it always uses all the cores for a small amount of time, but its execution time is 1/3, only 3 seconds. Why that? Because it's basically this time plus something more. So 2 seconds is the time to scan the column, not building the bitmap, plus you need to compute the if and do something more, and it goes to 3 seconds. Why do I show you this final example? The reason is because everybody, me included, reading books and blogs would say that this is the correct, no, that this is bad and this is good. But if you test it, and if you look at it, and if you look at the result, you will discover that you need to be creative. You need to imagine. You need to work with your imagination and try different formulas and different ways of writing code. Yes?
I have a question. In this square on the left side, we have if statement, not filter statement. Is there
Yes. Yes, this is an expression. If is a function in DAX that computes, as you might expect, if. So it checks.
In the query you ran, there was a filter.
Oh, it's the same in reality. Some X audience, it's the same as running the filter. You are right, the query is different.
I'm not sure whether it will give the same result. Maybe.
No, they give the same result. I guess I have the query with if somewhere. Yes, it's here. Okay. You need to run it. This is slightly slower. So in reality, what I guess is that the slide is wrong. Yes. So this takes 9 seconds. What I need to do is take this query, go to the slide, copy there. Okay. Imagine that I copied the slide there. And that's how it should work. No, this is the with filter is faster. The one with if uses formula engine, storage engine, creates a lot of other issues. But anyway, Marco was sent the right query. He gave me the wrong answer anyway. I didn't send it to Chris. It would have been fun. So I had another way of discussing with him. So if you plan to work with DAX with large data models, and if you want to play with, if you want to do optimization, the point is be creative. Don't trust the rules. Never trust rule of thumb. Read the blogs, read the books, or read whatever you want, but if you want to optimize and if you want to work efficiently with DAX, understand the internals and then apply the theory you learned. forgetting about MDX, forgetting about SQL, forgetting about everything else, just focus on DAX and tabular. Doing so, you will be able to run 4 billion rows on a laptop with good performance, and your customer will probably be happy. This data model, keep in mind, it's 4 billion rows, and it's somewhat small, it's not so large. The database of, not the database, but the analysis services database, okay, of the audience, it's not very large. It's 14 gigs. So 4 billion rows can stay in 14 gigs, and 14 gigs are cheap. You can buy them at the supermarket. They are not expensive. So if you have a customer which has, let's say, 20 billion rows of sales in his data model, you can go with tabular with good confidence. But before doing that, spend time, learn the theory, because otherwise you might be scared by something which is not really scary. The problem of tabular is not knowing the internals of the engine and not applying the theory when you go in production with the model. I am, whoa, only 8 minutes late. That's beautiful. If you have any question, if you have anything you want to know, if you want to know how to cook spaghetti, anything you want, I'm here to answer your questions. Otherwise, thank you very much for attending.